your exam? How was it?
Sir, exam was more or less fine. Personally what I faced was that time was not sufficient for me.
No, but time I have given you, right? Almost 3
Yes, sir.
hours.
Yes, sir.
That
Yes,
is
sir.
more than sufficient.
Regarding, yes, sir. Regarding that, you don't have anything. I mean, I was only a bit slow from the beginning. So.
Okay. Okay. So, so only question number 1 was unknown. Okay. Rest of the thing you could have done it easily. Okay. It's not that the question number 1 was slightly different, but that is also not. If you understood the tensor and if you understood Laurent transformation, you could have answered that question. Okay. So I will go through the question number 1. Okay. I will just highlight the essentials of question number 1, and then we will go to our usual topic. Okay. So in the question number 1, what I asked is the following. Let me see the question number 1. Yeah. So in the question number 1, I have given you the 2 coordinate system. Okay. These are not, so there is a coordinate system. So question number 1, internal examination. Okay. So I have given you a coordinate system which is usual one, that is x0, x1, x2, x3. Okay. And there is another coordinate system I am calling that as S1, that is x plus, x minus, x3, x2, and x3. Okay. And these coordinates are related to this one by following: x plus minus is equal to x0 plus or minus x1, and x2, x3 remains unchanged. So x2 equal to x2 and x3 equal to x3. Okay. So now your new coordinate system is this one. Okay. Remember, this is not Laurent transformation. Okay. Some students assume that this is Laurent transformation. This is not a Laurent transformation. I am saying that there are 2 coordinate systems. One is your Cartesian coordinate system and one is this coordinate system. There is no name, say S1. Okay. Now in this coordinate system, your metric is ds square equal to dx0 square minus dx1 square minus dx2 square x2 square plus dx3 square, right? This is your line element. Okay. This in the matrix form, you can write this as a metric, right? Eta mu in the matrix form will be 1, minus 1, minus 1, minus 1. Okay. Now I want to write metric, okay, in this coordinate system. So what it will be? It will be, what is your dx0? dx0, you can invert this relation. Okay. So you can determine x0 in terms of x plus x minus. So x0 will be, so it will be twice, if you add these 2 equations, so it will be twice x0 will be x plus x minus. So it will be half, x0 will be half of x plus x minus. Okay. And your x1 will be half x plus minus x minus. Right? Okay. So dx0 will be half dx plus dx. Okay. So it will be half dx plus minus dx minus. Okay. Now your ds square, right? Now your in this coordinate system S1, let me write that as ds tilde square. Okay. That will be, that is same as your ds square. Line element will be same. Okay. So you have to just replace dx0 square by this. Okay. So you have to square this quantity. you will see that cross term will survive and dx plus square, dx minus square will be 0, coefficient of that. Okay, so you can write this as half of dx plus dx minus plus half of dx plus dx minus. I could have written just dx plus dx minus, okay, but I want to write it in a symmetric form. That's why I put half here, okay, and minus dx2 square minus dx3 square. Okay, so in the matrix form, what will be the matrix? Okay, eta tilde mu nu will be, see, this we write as eta tilde mu nu dx mu dx nu, where mu nu runs from plus minus 2 3. So eta tilde mu nu will be 0, half, half, 0, 0, 0, 0, 0, 0, 0, minus 1, 0, 0, 0, 0, minus 1. Right? Okay. So this will be eta tilde lower mu nu. This implies eta tilde upper mu nu will be inverse of this. So this will be 2, 0, 0, 2, and rest of the thing as it is. Okay, so this, all these things is determined. Okay, so this is the part 1. Okay, now so given any 4 vector v mu, okay, in S1 coordinates, what will be v mu? That was the question. Okay, is this clear? This was the question. Okay.
Excuse me, sir.
Sir,
eta tilde 0 1 should be 2 instead of eta tilde 0 0.
Where eta tilde?
Upper, I mean the upper eta tilde mu nu. There eta 0 1 should be 2.
It is 0. Sorry, so it is 0, 2, 2, and 0. Yes, correct. Okay, so these are inverses of each other. So now, given a 4 vector v mu in S1, what will be its corresponding covector? Okay, so now v mu in S1 coordinate will be v plus v minus v2 v3. Agree? Okay. So basically, I wanted to ask, what is the raising and lowering operation in this coordinate with the metric given by this one? Okay, so basically, what is the raising and lowering? So question boils down to that. Okay, so let us see. So v mu will be eta tilde mu nu v nu. This will remain as it is. Okay, so this will be, so now you see, I will fix mu to be plus. Okay, so this will be eta tilde plus, if it is, then mu cannot eta plus minus is half of v minus. So your v lower plus is half of v upper minus. Okay, and similarly v lower minus will be half of v upper plus. Okay, and your v2 will be minus v2 and v3 will be minus v3. Agree? Okay, so this is your covector in S1 coordinate system. Half v minus, half v plus, and minus v2 minus v3. Okay, agree? I will see if there any other question remaining. Yeah. Okay, so this is basically raising and lowering. Okay. Now the next thing, I will come to the Laurent transformation and etc. after this. But next thing is energy momentum relation. Okay. What is your energy momentum relation? Energy momentum relation is P mu is m square c square. Okay. So this is nothing but, so in this coordinate system you can check now you since you know how to raise and lower, I can write this as P plus I'm just expanding this, P minus okay, plus P2 plus P3 this is equal to m square c square. Okay, so this implies now you know P lower plus in terms of upper indices. Okay, so P lower plus will be half of P upper minus. Okay, and P lower minus will be half of P upper plus. So they will add and gives me P plus P minus. Okay, and P lower 2 is minus of P upper 2, and similarly for this. So it will be P2 square minus P3 square equal to m square c square. That's it. Okay, this is what is expected. Now the DLM version. What will be the DLM version? Box is del mu. Okay, so this is del plus del minus is equal to what? Okay, so now we should know what is del lower plus in terms of the upper indices. Okay, clear? Okay, so del upper minus, so here you have to be careful. Del upper minus, okay, so conventionally we would like to keep lower indices on derivatives. Okay, normally we don't write this, we write minus of this. Okay, right? So let us try to evaluate what is del upper plus. Del upper plus will be eta tilde plus minus del lower minus. Okay, so eta tilde plus minus is twice del minus. Okay, and similarly del minus will be eta tilde minus plus del minus, so it will be twice of. Okay, so this implies this term will become twice of del minus del plus, and this will be twice of del plus del minus, so it will be 4 times del plus del minus, okay, minus del 2 square minus del 3 square. Okay, so this will be your DLM version. Okay, and hence now you can use this to form the plane Gordon equation. Okay, that we will see later. Okay, it's easy. You can form the plane Gordon equation. Okay. Now the next part is the Laurent transformation. In question number 1, part A, I also asked the Laurent transformation. How the Laurent transformation looks like in S1 coordinates. Okay, you know that in usual coordinates, x prime 0 is given. X prime 0 is x0 cos hyperbolic phi minus x1 sin hyperbolic phi, and x prime 1, it is a boost along x-axis, so only x0 and x1 is going to change. So x prime 1 will be minus x0 sin hyperbolic phi plus x1 cos hyperbolic phi. Okay, fine. Now it's easy job. So you have to just substitute the form of x0 and x1. Okay, you have to substitute these forms, this one and this one. Okay, so if you substitute that, okay, what you are going to get is x prime plus minus is equal to, okay, cos hyperbolic phi, okay, minus plus sin hyperbolic phi, and x plus minus. If you substitute that, okay, you will get correct result. Is this clear? So what I mean is the following. Okay, you define x prime plus as x prime 0, okay, plus x prime 1, and you just substitute this here and collect the terms, collect the coefficient of x0 and x1. You will get, and again use the definition of x minus. You will remains unchanged. 2 is equal to x2 and x prime 3 equal to x3. Okay, these two components remain as because it is a boost along x-axis. Okay, so what it suggests is that your x plus coordinate, see, this transformation suggests that your x plus coordinate now become x prime plus, which is some factor times x plus, and your x minus goes to x prime minus, which is some factor, say this is lambda 1 and some factor lambda 2 times x minus. So it is sort of scaling, right? Okay, the overall multiplicative factor is called scaling. Okay, so you have a vector, you scale it to either larger magnitude vector or smaller magnitude vector. So this is, direction is not changed, but the magnitude has changed. Okay, so it is some sort of scaling. Okay, and x2, x3 remains unchanged. So it is a scaling in your x plus minus coordinate. Okay, but what is the meaning of x plus minus? If you see carefully these coordinates, okay, these coordinates x plus minus definition, these are actually x plus and x minus are actually null coordinates, right? These are basically null coordinates. Is this clear? Okay, because what I'm doing, I have x0 here, x plus here, x1 here, okay, x1 here. Forget about. I'm okay, and x0 minus x1 will be this. Okay, so these are basically null coordinates. You can see that from the following point of view also, by using the definition of null coordinates. Okay. Suppose I have a vector, 4 vector, which is this x plus 0, 0, 0. Okay, then what will be v mu, v mu? So v mu will be v plus plus v minus plus v2 plus v3. Okay, now what is v plus? Okay, so v plus is basically we can either raise this plus or lower this plus. Okay, so this will be half of, okay, so let me raise it. So this will be, okay, according to this thing. Okay, so yeah, so this will be half of v minus, so it will be half of v plus v minus. Okay, clear? Plus this will be v minus, so it will be half of v minus v plus. Okay, plus this will be, you can calculate this. Okay, but now you see the component. Okay, v plus is x plus, and rest of the things are 0. Okay, so this will be 0 always, right? So this quantity is a null vector. Okay, so this quantity taken as a vector is null vector. Similarly, this quantity is also a null vector. Okay, so I have the null vector. So this basically represents null vectors taken as a vector. Okay, and this what this tells us. So I have null vectors. Go to light cone. Okay, and under Laurent transformation, they will be at most they will be scaled. Okay, so under Laurent transformation, so let me go to next page. Okay, I have null vectors. Okay, let us say these null vectors are these and this one. Okay, and under Laurent transformation, okay, these are going to scale just. It may elongate or it may shorten. Okay, but there will be scaling. So what is happening under Laurent transformation? This angle remains same, right? Okay, so the light cone, the essence of this problem is that the light cone remains light cone under Laurent transformation. So in 3 dimension, you have this light cone. Okay, under Laurent transformation, it does not happen that this will become like this. Okay, this is not going to happen. This angle will remain same between null vectors. What this tells us is that the angle between null vectors will remain same. So this is not going to. So a light cone will not shut or light cone will not broaden under Laurent transformation. This is the interpretation of this. You can calculate also the angle. Okay, how you calculate the angle? Normally in 3-dimensional geometry, how you calculate the angle? V dot V is square cos theta, or V dot W is equal to magnitude of V, magnitude of W, cos theta. Okay, so angle is always defined as, so this will be angle cosine will be defined as V dot W and magnitude of V, magnitude of W. Okay, now here in 4 dimension, definition of V dot W is going to change. So this will be eta mu nu, V mu, W nu, and this will be V mu, and then, so this basically gives you the angle or cosine or whatever, it may be cos hyperbolic also. But this quantity remains unchanged. In other frame also, this will remain same under Laurent transformation. Okay. So is this problem clear? This is how you should approach. Okay. Clear? So this is basically the exercise in raising and lowering, understanding of 4 vectors, okay, and Laurent transformation. Okay.
Sir, can you go to the next slide?
Next.
Sir, yeah. Yes, sir, here we saw V mu is just 0. So how do we really calculate the angle?
No, for this particular vector, it is 0. So it is a null vector basically. This tells us that this is a null vector. Okay. This I am saying for any general vector. Okay. This is for any general vector. Okay. This happens. This happens for null vector. Okay. Is that clear? This is the definition of null vector. This should, if a vector is null, then this should happen in any coordinate. This is what it tells. Now, to see that the angle is not changing, what you need to do, okay? Angle is not changing means at max what happens? That means the vectors are either two vectors. See, you imagine two vectors in 3D. And I'm saying that there is a transformation which does not change the angle between two vectors. Okay. Then what could be the transformation? That transformation is only scaling. Okay. Yes.
Yes, sir. Okay.
And this is what we are getting here. If the transformation is only scaling, see, there is no x minus dependence here. Okay. X prime plus depends only on x plus, and x prime minus depends only on x minus. There is no. So this vector will, depending upon this lambda 1 and lambda 2, this vector will either increase its length or decrease its length. That's it. But
yes, sir.
there is no meaning to say increase or decrease because the length is always 0, in the sense that it is a null vector.
Yes, sir. Even I tried taking the inner product of transformed x plus with transformed x minus. It just gives a inner product of our original x plus and original x minus, because
that is bound to happen. Yeah, that
yes,
is bound to happen.
Lambda 1, lambda 2 is 1.
Yes, but no. That for that you don't have to go to x plus x minus coordinates. Okay. See, you should understand that why I am going to x plus x minus coordinate. This in x plus x minus coordinate, the null directions are separated out. Okay. Your null directions are separated out now. Suppose if I send the light signal from here, it will either travel along x plus or x minus. Okay, because this is a light cone. Okay, and light rays travel on the edges of light cone. Okay, so it will be x plus x minus, but now it is a cone. So that conical part will be taken care by this x2, x3. You can write in polar coordinates. Okay, and you can basically revolve this figure. Okay, what you will obtain is a cone. Okay.
Yes, sir. Okay.
So besides this, this problem also tells you how to raise and lower. It also tests your knowledge of raising and lowering. Raising is not under raising, it's not that you will always get lowering of this. Is not guaranteed to be plus or minus this. That is what it tells. You could get different. Okay, fine. And now you can use this expression to write the Klein-Gordon equation. Okay. What is basically the Klein-Gordon equation? It is 4 times del plus del minus phi minus this del 2 square plus del 3 square acting on phi equal to 0, equal to m square c square divided by h power square, some constant factor. Okay, fine. Now how to write the plane wave solution? Plane wave solutions, you have e to the power plus or minus I p mu x mu, right? Since the invariant form, it holds in any frame. Okay, So we know now how to raise and lower. Okay, so you can write this as p plus x minus plus p minus x plus etc. in that. So this will be your plane wave solution. That's it. You can use your usual plane wave solution and transform into S1 coordinates, or you can start from you can directly start from plane Gordon equation in S1 coordinates and solve that. Okay. In passing, I should tell that suppose if you have a situation where m is 0. You see where this is useful. Suppose if you have a situation where m is 0, then what is your equation? Box plus n square c square phi equal to 0. Okay. I may be wrong with these constants. Okay. You can check. If n is 0, this term will go away. Okay. So box phi equal to 0. Okay. Now you assume that phi x0, x1, x2, x3 depends only on x0, x1. Suppose for a moment there is no x2, x3 dependence. Okay. So how this equation look like? Okay. So you have you go to x plus x s1 coordinates. So this will be 4 times del plus del minus phi, and that del 2 del 3 acting on this phi will be 0 because there is no x2 x3 dependence. So this will be 0. So now you have this sort of equation. Okay. So it is del plus del minus phi equal to 0. What is the solution of this? In this case, your phi can be written as phi which depends on a part which depends only on plus coordinate, and another phi which depends only on minus coordinate. This is the most general solution, right? Because if you substitute three ways, because if this plus, when I add del minus on this, I will get 0, and when I add del plus on this, I will get 0. Okay, so this solves this equation. So that means your general solution will be some function x plus 6 x0 minus x1. Okay, plus some g of x0 plus x1. So this is basically your wave solution, right? T minus, if you substitute properly c and etc., c and k etc. Okay, so you will get t x minus vt kind of thing. Okay, you know that plane wave solution must have this dependence x minus vt, traveling wave. This is coming here, and now that is explicit. So sometimes it is better to use S1 coordinate system, and it is especially useful when mass is 0, and you can see why. Because if mass is 0, then this equation decouples. Okay, direction. And basically mass is 0 means you are concerning the massless particle, which is nothing but the electromagnetic. The known thing is electromagnetic, but there could be other massless scalar particles. Okay, for that you can use. So this is the essence of question number 1. Okay, and the last part of question number 1 that is also useful. Okay, last part of your question number 1 is you have T3P obviously is not Lorentz invariant quantity. Lorentz invariant quantity. Okay, and now I asked you to determine what is the Lorentz invariant volume element. 3 volume element. So I said that the 3 volume element as it stands is not Lorentz invariant. Okay. Now what should be the Lorentz invariant measure? Okay. For that, you consider this D4P. Okay. 4-dimensional volume is Lorentz invariant. That you know. Okay. 4-dimensional volume element is Lorentz invariant. Okay. So D4P stands for dP0 and D3. This is Lorentz invariant. Okay. So now you have to go from here to here with some factor, so that this quantity under Laurent transformation should not change. So what should be that quantity? Okay, you can easily guess it is proportional to 1 over gamma, but I don't want the answer in gamma. So what you can do, you consider the following: D4P, okay, and you say that your P0, this is momentum. We are not in real space, we are in momentum space. Okay, so your P0, we have this relation, right? P mu equal to m square c square. Okay, so I will take this condition up into account by writing as delta function, 4-dimensional delta function, and P mu minus m square c square, right? That means if this condition is satisfied, then and only then I will get non-zero answer. Otherwise, I will get zero answer, because delta function is, if this is not equal to this, then I will get 0. Okay, if this is equal to this, then I will get delta 0 and I will get, that is 1. Okay, so it has a, so this condition is taken into account, and we are concerning about P0 greater than 0. Okay, so now this means D3P dP0. Okay, and this I can write as delta function P0 square minus vector P square plus m square C square. Okay, P0 greater than 0. Okay. Now you concentrate on this part. What is delta of fx? You use the property of delta function. Delta of fx is delta of x divided by f prime of x evaluated at zeros of f. So xi are the points where f of xi equal to 0. So this is the property of delta function I'm using. Okay. So what is delta of? Assume this as a function of p0, entire thing. Okay. So this I can write. So delta of p0 square minus p square plus m square c square is equal to, you think this as a function of p0, so this will be delta of p0 divided by derivative of this evaluated at the zeros of this function. Zeros of this function is this, right? So it is twice p0 evaluated at p0 equal to plus or minus p square plus m square c square. Okay, but minus signs is overruled because of this. Okay, so I will get only plus sign. So this is equal to delta P0 divided by twice of E. Right? This is your energy. Okay. So now you integrate over P0. What you are going to get is just 1 or twice. And then there is a 3 integration. So this will be, so that means that D4P delta of P mu minus m square c square for p greater than 0 is nothing but D3P divided by twice. Okay. But we know that this is Lorentz invariant quantity. This quantity is Lorentz invariant. So this quantity is also Lorentz. Hence this acts as, so D3P divided by twice E acts as a Lorentz invariant measure. So Lorentz invariant volume element. Okay, in P space. Okay. Yes. So I hope question number 1 is clear. Any doubt regarding this? Any question? Is it clear to all?
Yes, sir.
Okay. So this is slightly off the track. Okay. The question number 1. Okay. And rest of the questions were in the line of your classes. Okay. Whatever we did in the class, okay, it's there. A slight variation in that. Okay. So I would suggest you to go back again and solve entire paper, okay, for your understanding. Especially the question number especially the question number 3. Okay, question number 3 of your paper. Okay, that will be useful in future also. Okay, question number 5, it's simple. Okay, the last part of the question number 5. Okay, have you understood the last part? In a certain, so I said that write f mu nu in a matrix form, define a tensor f tilde as half of epsilon and f, combination of epsilon and f. Okay, then write f tilde mu nu and f tilde lower mu nu in matrix form. Okay, then show that f tilde mu nu f mu nu is minus 4 times E dot B. Okay, and after that I asked, suppose there is a certain Lorentz frame in which electric and magnetic fields are perpendicular to each other. So the question is it possible to find another frame in which vector E is not perpendicular to vector B? What is the answer? Has anybody answered this?
It is not possible, sir.
Why it's not possible?
Because it is a Lorentz scalar, so E dot B should be constant. So it should be 0
No.
in any other
Where
frame.
you got that E dot B is Lorentz scalar?
Because we constructed it f mu nu, we contracted the tensor f mu nu, f tilde mu nu, f mu nu.
F tilde mu nu?
F mu nu. That is the contraction. So that will be Lorentz scalar.
Correct. Okay. So that's why I gave you that quantity f tilde mu nu, f mu nu. So this is Lorentz scalar. Okay. So if it is true in one frame, then it's true in all frames. So E dot B is 0 in one frame. It is given to you. Then it will remain to be 0 in any other frame. So if you construct a frame in which E and B are perpendicular to each other, then in any Lorentz frame, your E and B will remain perpendicular to each other. Okay. Right. And in question number 4, the hint is that determine the so you have to determine the relative velocity. Okay. When in a certain Lorentz frame, static uniform electric field E0 is parallel to x-axis and static uniform magnetic field B0 lies in xy plane, making an angle theta with x-axis. Determine the relative velocity of reference frame in which electric and magnetic fields are parallel. What the hint is, in the suppose E prime, vector E prime and vector B prime are the electric and magnetic fields in transform frame. We want that E prime and B prime to be parallel to each other. That means cross product of E with B must be 0. Okay. So you construct the frame in such a way that E cross B, E prime cross B prime is 0. So you'll get a one condition. That condition one can translate on the condition of velocity. Okay, that is the hint. So the hint is that you construct a frame in which E prime cross B prime is 0. Okay. Okay, so this is the brief discussion of your question paper, and I hope the questions are clear. Okay, and my suggestion is that you again try to solve entire paper, okay, without looking into any reference for your understanding. Okay. In fact, what you can do, you take question number 1 and do whatever we learned so far in S1 coordinates. That will solidify your knowledge about and working knowledge about tensors. Whatever we did so far for Klein-Gordon equation, current densities, electromagnetic field, Maxwell's equation, whatever we did, you just write everything in S1 coordinates. So in between here, you have to define epsilon tensor. Okay. So you think a way, think how epsilon tensor can be defined in plus minus coordinates. Okay. Good. Okay. So now we will go back to our course. It's already 1:15. Okay. Now, so far what we have seen is that to include the principle of relativity into quantum mechanics, okay, one of the possibility is Klein-Gordon equation. Okay, so now, so what we are studying, we are studying the quantum mechanics with which is consistent with the laws of special relativity. Okay, so we constructed the Klein-Gordon equation, which is consistent with laws of special relativity. Okay, it is consistent with the energy condition, E square equal to P square, C square plus M square C to the power 4. Okay, the drawback of this is that the probability density may be negative, and we have positive as well as negative energy solution. Okay, to free relativistic particles. Okay, so this tells us that I cannot interpret this phi Klein-Gordon wave function, Klein-Gordon function phi as a wave function. I cannot use directly. Okay, but still you overlook this problem and try to solve the Klein-Gordon equation in different potentials. You can couple the Klein-Gordon equation with electromagnetic field via principle of minimal coupling. Okay, in the non-relativistic limit, it gives you the Schrodinger equation coupled to electromagnetic field. Okay, you consider Schrodinger equation. Okay, and you introduce the electromagnetic interaction. You must have seen that in quantum 2. What is the Hamiltonian for Hamiltonian for a particle, for a charged particle coupled to electromagnetic field? Okay. Hamilton in the Schrodinger equation. So you will get the same equation if you take the appropriate non-relativistic limit of the Klein-Gordon equation. Then you specialize the potential. You assume that vector potential is 0 and my phi is central potential. Your scalar potential is central potential. Then you can solve that equation. This will give us the atom-like solution, hydrogen atom-like solutions, but with the correction. That correction is basically relativistic correction. Okay. I will give that exercise in the next semester as a lab. So, but these two problems are central. So now, and this problem occurs due to the second order nature of Klein-Gordon equation. Okay, due to the second order nature of the Klein-Gordon equation. Second order in time as well as second order in space. How we got the second order terms? Because we started with this relation. Okay. And we use the correspondence principle and replace E by I h cross del L T. Then E square will be h minus h cross square del 2 by del T square. So that's how we got the second order differential equation, partial differential equation. Okay. Clear? Because of that, okay, your rho is phi star del T phi minus phi del T phi star, something like that. There is some factor. Okay. So this, when this term exceeds the first term, rho becomes negative. But now let us construct. So now our aim is to construct an equation which looks like Schrodinger equation, del psi by del T equal to h psi. Okay, but it should be consistent with E square equal to P square C square plus M square C to the power. So this equation should be consistent with this. So now I demand that my equation satisfied by psi is of this form, but it is consistent with this. Okay, so this is my demand. Okay, my claim is this, and I demand that it should be consistent with this energy condition. So what should be the h? Okay, or what should be? Okay, let us not call this as h at the beginning. Okay, let us put something here acting on psi. What should be this? That is the question. Okay. Let us consider the following linear combination. Let us consider I h cross del psi by del T equal to minus I h cross. This is for convenience. We will understand why these factors are there. Okay, C, and let us put some alpha k, okay, pk. These are your momenta. Okay, plus some beta mc square. Okay, and this will act on psi. Okay. There. So these alpha k's, later on it turns out that this alpha k's must not be number, just your usual numbers. If it is usual number, then this condition is not satisfied. We will see that. So I am considering this form. Okay. So yeah. So instead of since I introduced this IH cross, I should not write this PK. So it should be in actually partial. Okay. So my demand is that any equation governing psi must be consistent with this, and it should be relativistically covariant. That means it must have the same time, same order of time and space derivatives. Okay, so these two are the guidelines. Okay, so we have first order in time and first order in space, and I am taking some linear combination of the spatial derivatives. Okay, yes, and I demand that this equation is consistent with this equation. Okay, so let me call this as, so let me first write this. Okay, so minus I h cross del k is just pk. Okay, so minus I h cross del k is just pk. So this I will write as c times alpha k pk plus beta mc square acting on psi. So this is a momentum operator. Okay, so this you can write as c times vector alpha dot p plus beta mc square. But till right now, I don't know anything about this alphas and beta, except the fact that there are alphas are 3 in numbers. Okay, that means k runs from 1 to 3, because we should have 3 spatial derivatives. And beta is just a single quantity. Apart from that, I don't know anything about it. Okay, alpha, later on it turns out that alpha k's are not numbers. Okay, so let us consider this I h cross del psi by del t. Okay, now for this to be consistent with this, okay, we must have, if I call this quantity as h, okay, we must have h square psi must be equal to e square psi must be equal to p square c square plus m square m square c to the power 4. Okay, clear? Fine. So let us see what is this quantity. Okay, if I square this quantity, okay, so c alpha dot p, okay, plus beta mc square, and I will square it. So that means I will multiply it twice. And this I will equate it with, this is the operator relation. Okay, so this quantity must be equal to this, provided we act on psi. Okay, so I will equate this with p square c square plus m square c to the power 4. The meaning of this equation is that when these two acts on psi, okay, that must is equal to this quantity multiplied with psi. This is just a number. Okay, clear? So let us multiply it. Okay, so I will get c square alpha dot p alpha dot p. So this will be alpha I pi sum over I implied, and then this will be alpha j pj sum over j implied. Then I will get n cube beta MC cube, okay, then alpha dot p into beta. So alpha I beta pi. Pi is just your number. Is pi. Okay. Plus I will get MC cube. Okay. Beta alpha I pi from this. This multiplied with this. Okay, that is this term. Plus beta square m square c to the power 4. This is equal to p square c square plus m square c to the power 4. Okay, is that clear? Okay. Now you collect the coefficient of c, powers of c. What is going to happen? Okay, I can write the first term. Okay, what is my first term? Alpha I pi alpha j pj. Since pi pj's, okay, I can write this relation as alpha I alpha j pi pj. Okay, this is further equal to alpha I alpha j, okay, plus alpha j alpha I divided by 2, okay, and pi pj. This is same as this. I have just written in different form. Okay, because pi pj is symmetric. Okay, whether I write pi here or pi here, it doesn't matter. That is what I used. Okay, therefore my last equation, this equation becomes, I will rewrite this, c square into alpha I alpha j plus alpha j alpha I divided by 2 pi pj plus c cube mc cube mc cube, and then I have alpha I. So I will combine these two terms. Okay, alpha I pi into alpha I beta plus beta alpha I. Pi into alpha I beta plus beta alpha I, okay, plus beta square m square c to the power 4, beta square m square c to the power 4. This must be equal to p square c square plus m square c to the power 4. Okay. Now you compare the coefficients, the powers of c. If I collect the power of, if I collect the coefficient of c to the power 4 term, it tells us that beta square must be identity, right? Okay. Beta square must be 1 if you collect this with this. Okay. This is important. This tells us that these alphas and betas are not just usual numbers. They are basically matrices. It turns out that they are basically matrices. What it tells, okay, there is no c cube term here. Okay, so this tells us that alpha I beta plus beta alpha I is 0. Now, if it is a usual number, then this equation is inconsistent, right? If it is usual number, say alpha is 5 and beta is 9. Okay, 5 into 9 is minus of 5 into 9. That is nonsensical relation. However, if I say that alphas and betas are matrices, then this could happen. Okay, so this tells us that alpha I and beta are matrices. It is a possible. It is a possibility. One of the possibilities. Okay. Then only then I will get 0. For usual numbers, I will not get 0. Even for usual functions also, I will not going to get 0. Okay. And this tells us that coefficient of c square term is p square. So I must have delta I j here, twice of delta I j. So this is, so matching the coefficient of c square will tell us that alpha I, alpha j plus alpha j, alpha I must be equal to twice of delta I j and identity. Okay. This delta I j tells us that this is equal to 2 times identity when I equal to j. If I equal to j, so this delta I j will always combine with this. Okay, so this will give me p square. Delta I j, pi, pj is just a p square, vector p square, because it will be p1 square plus p2 square plus p3 square. So this is p square. Okay, clear? And this identity is because the left hand side is a matrix. So now this identity which I am writing is basically the identity matrix. This tells us that beta square is 1. It could be number 1, it could be identity matrix. Okay. Second condition tells us that these alphas and betas are basically matrices. That's why this identity is the identity matrix. Similarly here, if I write just 2 times delta ij, the left hand side is a matrix, right hand side is a number. So I have to put some identity here. Okay, clear? So in order to satisfy this relation, we have these conditions. What are the conditions? We have set of 4 matrices, satisfying beta square equal to 1 identity and anti-commutator. This basically means the anti-commutator of alpha I, alpha j equal to twice delta ij times identity, and anti-commutator of alpha I beta must be 0. So this is this one, this is the last one, and this one is the second. Okay, so these are the properties for these alphas and beta. Okay, when satisfied, okay, I will get the consistency between I will get the consistency of this equation with this. Is it clear? Is that clear? Okay. Is this algebra clear?
Yes, sir.
So the fact that these alphas and betas are matrices immediately tells us that this psi here is not a usual function then, right? It must be some component vector, some column vector, right? It's not usual function, it will be some column vector function. Okay, so this tells us that this psi must be of some column vector. I don't know what is this column, because in order to make sense of this equation, okay, if these are the matrices, then they should better act on column vector. Clear? So let us see how that happens. Okay. But first of all, is this clear? Okay. That if I claim the first order equation for a relativistic particle, okay, then to make that equation consistent with energy momentum relation, okay, we must have these kind of objects. We must introduce objects like alphas and beta which satisfy this relation. Okay. This equation is called Dirac equation. Okay. So this is what Dirac did. Okay. So Dirac equation is IH cross del T psi equal to C times alpha dot P, okay, plus beta MC square psi, okay, where alphas and betas are matrices satisfying the following relation, following algebra. Normally we say this as algebra. Okay. Also, if I want to give status of Schrodinger equation to this, so this is nothing but H psi. Okay. If I want to give this H a quantum status, okay, then H must be Hermitian, right? Okay. So the Hermicity of H implies, okay, implies what? Okay, implies that alpha I dagger must be equal to alpha I and beta dagger must be equal to beta. So these are Hermitian matrices satisfying this relation. Okay. But still we don't know anything about these matrices. Okay, we don't know what form they take. Okay, even we don't know what is the dimensionality of these matrices. Right? I don't know anything about this. I know only the following things. These are the matrices. Okay, they satisfy these anti-commutation relations, and they are Hermitian. That's it. Okay.
Sir, sir, they are Hermitian. This is our means claim as a sort of assumption, or means how we are.
No. I want to give this. Now I'm saying that it is a quantum equation. It is like your Schrodinger equation. Okay. Your Schrodinger equation is what? I H cross del psi by del T equal to H psi. And this Hamiltonian is Hermitian quantity, right? It is observable. Right? So I demand that this H is Hermitian. I want to do the same thing that we did for Schrodinger equation, except the fact that these are not numbers. That's it. That is the only difference. Is that clear?
Yes, sir.
Okay. So now let us see what these matrices are. Okay. First of all, okay, let us concentrate on this relation. So I have the properties of beta, properties of alpha I and beta. Okay, let us concentrate on this relation. So alpha I anti-commutator of alpha I with beta is equal to 0 means alpha I beta plus beta alpha I equal to 0 implies alpha I beta equal to minus beta alpha I implies, okay. Suppose if I multiply from the right by beta to this relation, multiply from the right, so I will get alpha I and I will get beta square, but beta square is 1, okay. So alpha I times identity, that is alpha I. So alpha I equal to minus beta alpha I beta. Agree? Clear? So if I take a trace of this, okay, trace of alpha I, okay, what I am going to get? Minus trace of beta alpha I beta. Okay, but trace of, now you should know this relation. Okay, trace of A B C is same as trace of C A B is same as trace of B C A, cyclic ordering. Okay. Okay. So this is equal to minus the trace of beta beta alpha I. But beta beta is beta square, that is 1, so it is alpha I. So this implies that trace of alpha I is 0. So alpha I are traceless matrices. Okay. Clear? Similarly, if I multiply this relation from the right by alpha I, okay, so what I'm going to get? Alpha I beta alpha I equal to minus beta alpha I square. No summation over I. It just, if it is, if I is 1 here, then I will multiply by alpha 1. If I is 2, then I will multiply by alpha 2, and so on. Okay, so this is equal to what? Okay. Alpha I beta alpha I equal to minus beta alpha I square. Okay, so this implies, so this thing implies that the see, alpha I square is what? Okay, from this relation, okay, alpha I square, okay, let us calculate. Alpha I square will be anti-commutator of alpha with alpha. If I take, then it will be alpha twice alpha I square equal to twice delta Ij. So delta Ij will be 1 in that case, identity. So alpha I square is just identity. Okay, so here this alpha I square is identity, so it is minus beta. So this implies trace of beta equal to minus of trace of alpha I beta alpha I. Okay, this is nothing but use the cyclic property of trace. So it will be alpha I beta trace of alpha I beta, but alpha is alpha I square, that is 1, so it is minus of trace of beta. This implies that trace of beta is 0. Okay, so I have traceless Hermitian matrices. That is what I know now. Okay, satisfying this anti-commutation relation.
So,
Okay.
could you please repeat how did you get the trace? How did you get alpha square is equal to identity?
No, I cannot hear you. Can you repeat the question?
Hello.
I cannot hear you. Can you repeat the question? Yes.
Sir, could you repeat please? How did you get alpha I squared as identity?
Alpha I square is identity. How I get alpha I square as identity? So I know that alpha I alpha j is equal to twice delta is a identity, right? So put, instead of j, put alpha I. This implies that alpha I anti-commutative with alpha I equal to twice delta I. Delta I is just one, okay, identity, right? Okay, so this implies that alpha I anti-commutative with alpha I is what? Alpha I plus alpha I. That is twice of alpha I square, right? Okay, so twice of
Okay.
alpha I square equal to twice of identity. Hence the result. Okay?
Yes, sir.
Clear?
Thank you, sir.
Okay. So now I know that these matrices are traceless Hermitian matrices. Okay. So at this point, we know that, so this implies that beta and alpha I are traceless and Hermitian matrices. The fact that these alphas and betas are Hermitian tells you what? Okay, it tells that these alpha i's and beta can be diagonalized. Right? Because you know that any Hermitian matrix can be diagonalized. Is this clear? Okay. Suppose alpha tilde I and beta tilde are their diagonal forms. Okay. Suppose if I diagonalize this matrix alpha I will get alpha tilde I. And after diagonalization of beta, I will get, say, beta tilde. What do I mean by these matrices are diagonal? All the diagonal elements are non-zero and the rest of the elements are zero. Right? Okay? Is that clear? Okay. This fact together with the fact that alpha I square equal to beta square equal to identity tells us that these diagonal matrices must have plus and minus 1 as their diagonal entries. Okay, implies if alpha tilde I and beta tilde must have plus 1 and minus 1 as diagonal entries. Right? I don't know how many plus 1s are there and how many minus 1s are there because I don't know the dimensionality of this matrix. Is this correct? Okay. Are you following what I'm saying?
Yes, sir. Okay.
Okay. Now the fact that these alphas and betas are traceless implies that there must be equal number of plus 1 and minus 1, right, in that matrix. In this alpha i's and beta alpha I tildes and beta tildes, there will be equal number of plus and minus 1. Agree? Okay. This implies that this alpha I tildes and beta tilde must be even in nature, must be even dimensional. Agree? Okay. Because then only then I will get equal number of plus and minus, right? Okay. This implies this original matrices alpha I and beta must be even dimensional. So I know now one more property, that this alpha I and beta are traceless, Hermitian, and even dimensional. Okay, that means they could be 2 cross 2, they could be 4 cross 4, 6 cross 6, 8 cross 8, etc. Is this clear? Okay. Now you consider space of n cross n traceless Hermitian matrix. Okay, let V be a vector space of n cross n traceless Hermitian matrices. Now, answer me the following question: what is the dimensionality of V?
n by 2.
N by 2. See, the Hermitian means they could be complex matrices. Okay. Suppose if I have 2 cross 2 matrix, okay, 2 cross 2 Hermitian, A, B, C, D. Okay, Hermitian means what? Okay, this A dagger equal to A, B, C, D. Okay, this implies what? These are the complex entries. Suppose if I say that I have a space of 2 cross, I have a space of Hermitian matrices only. So how many independent entries this matrix will have? How many independent real entries this matrix must have? Okay. So this dagger, okay, so it will be A, I can write as say A1 plus I A2. Okay. B I write as B1 plus I B2. C I write as C1 plus I C2. And D I write as D1 plus I D2. Okay. This dagger is equal to A1 plus I A2, B1 plus I B2, C1 plus I C2, and D1 plus I D2. Okay. It's dagger. This means A1 minus I A2, C1 minus I C2. Okay. Then B1 minus I B2 and D1 minus I D2. Okay. So this equal to this. So how many entries must be there? Independent. How many real numbers must be there? What it tells? Okay. This is equal to A1 plus I A2. That means A2 is 0. Right? Similarly, D2 is 0. Okay. This equal to this. It gives me one condition among C1, C's and B's. Right? Okay. So I have A1, A2, okay. Sorry, A1. Let me write. So I have A1, then I have D1, okay. Then I have C1, C2, B1, B2, okay. But then I have this equal to this and this equal to this. Okay. There are these conditions. Okay. So ultimately, how many real entries I will have? Now you can tell. What is the answer?
4.
4. Okay. So ultimately I will have 4 entries. So space of 2 cross 2 Hermitian matrices is 4 dimensional. It is same as space of your 2 cross 2 real symmetry. You consider real vector space, okay, of 2 cross 2 matrices, it will have dimensionality 4. So if you consider complex matrices, complex 2 cross 2 matrices with Hermicity condition, I will get dimensionality 4. Now I have one more condition, that is traceless. Okay, first you tell me generalization of this. So if I generalize this to n dimension, what is going to happen? What is the dimensionality of space of n cross n Hermitian matrices, just Hermitian? It will be n square, right? Okay, space of n cross n Hermitian matrices will have dimensionality n square. Okay, and then I have tracelessness condition, that is n square minus 1. So the dimension of space of traceless Hermitian matrices will be equal to n square minus 1, right? Okay. Now how many matrices we want? These are 3 numbers and beta is 1. So I need 4 independent matrices. Okay, because obviously they should not depend on each other. Yeah, otherwise there is no sense to this equation. Okay. So I want 4 matrices, right? Okay. Suppose my n is 2. Okay. We already proved that this n must be even. Okay. Suppose my n is 2. Okay. Then dimension, okay, of this will be 3. So I have a 3-dimensional vector space that I cannot accommodate these 4 matrices. Right? It's 1 extra. Right? See, these matrices must be the element of this vector space. You will try to understand. This is the vector space of n cross n traceless matrices. That dimension of that vector space is n square minus 1. Now I have this alpha 1, alpha 2, alpha 3 and beta. These are traceless Hermitian matrices. Okay. That means these matrices are the elements of this vector space. And we have to fix n. Okay. If n equal to 2, then dimension is 3. That means I cannot have 4 independent matrices. Right? Okay. So the minimum dimension that I should consider is n equal to 4. Okay. Then dimensionality of this vector space is what? 4, 6, 15. Okay. So in the 15-dimensional vector space, I can easily accommodate these 4. Right? We'll see what these 15 matrices are. We'll see that. Okay. But it is guaranteed that these matrices are now accommodated in that vector space. This means that the minimum dimension, okay, so this implies that alpha i's and betas are alpha i's and beta, okay, must be at least 4 cross 4 matrix. Okay. Minimum dimension. Okay. So this alpha I consists of alpha 1, alpha 2, alpha 3, and then I have beta. All these are 4 cross 4 matrices. Okay. Now we come back to this. Okay. Since this is a vector space, okay, one can easily show that the set of all n cross n traceless Hermitian matrices form a vector space. They satisfy axioms of vector space. One can easily show that. So since it is a vector space, okay, of dimensionality n square minus 1, we must have basis. Okay. So now you see the form of alpha 1, alpha 2, alpha 3, and beta depends on what basis we choose. Okay. So there is one specific basis which is called standard basis, standard or Dirac basis. Okay. In which sometimes it's also called standard or Dirac representation. Okay. You understand that the nature of this the form of alpha I and beta depends on what basis we choose. Like the form of any column vector AB depends on what basis we choose for R2. Okay. Similarly, the form of this matrices will depend on what basis we choose. Okay. So in this basis, okay, your beta is set to 1 minus 1. These are 2 cross 2 matrices. This is 2 cross 2. This is 2 cross 2. 0, 0. Why this minus 1? Because it should be traceless, obviously. Okay. So 2 cross 2 identity, 0, 0, minus of 2 cross 2 identity. And your alpha I is set to 0, sigma I, and 0. Where sigma I are usual Pauli matrix, Pauli spin matrix. Okay, so sigma 1 is 0, 1, 1, 0. Sigma 2 is 0 minus I, 0. And sigma 3 must be 1, 0, minus. Okay. We could have chosen different bases. Then I would have got different form. For a given problem, okay, it depends on what problem we are discussing. In this representation, it is easy to understand the Dirac equation in non-relativistic limit. It is easy to solve Dirac equation for center of force problem. In some another basis, there are some other interesting properties of Dirac equation, which you cannot see in this basis. But that is the property of basis, right? Some basis is good for some problem, some basis is bad for solving that same problem. Okay. So I have now 4 cross 4 traceless Hermitian matrices satisfying this relation. Okay, these relations. Okay. Fine. So any question so far?
Sir, Sir,
Yes.
hello. Sir,
Yes.
can you explain this part again, that why this alpha and beta must be 4 by 4 matrices?
Or see, we agreed that the dimensionality of space of traceless Hermitian matrices is n square minus 1. Okay. We also agreed that this the alpha i's and beta are traceless Hermitian and even dimensional. That means they could be 2 cross 2 or 4 cross 4 or 6 cross 6, etc. Okay. So I need a vector space which is big enough, which should accommodate these 4 matrices. What are these 4 matrices? Beta and alpha 1, alpha 2, alpha 3. Okay. So I need 4 independent traceless Hermitian matrices. Okay. Now let us consider the space of traceless Hermitian matrices. That space has dimensionality n square minus 1. Okay. If n equal to 2, then dimensionality of this space is 3. That means I cannot have 4 linearly independent vectors in 3-dimensional space, right? Okay. So I cannot have 4 independent traceless Hermitian matrices in okay, I cannot have 4 2 cross 2 linearly independent traceless Hermitian matrices. So the next minimum dimension is n equal to 4. Okay, dimensionality of that space is 50. Now in this space, I can easily accommodate 4 linearly independent matrices, which are traceless and Hermitian. Okay, so that's why these alpha i's and betas must be at least 4 cross 4 matrices. At least 4 cross 4. They could be 6 cross 6, could be 8 cross 8, and so on. Okay. Okay. Is this clear? But it turns out that this 4 cross 4 is sufficient. It will accommodate all the physics of Dirac equation. Obviously, one can go and construct the higher dimensional representation. Okay.
Yes,
So
sir.
I have now. Okay. So I have 4 cross 4 traceless Hermitian matrices. In the standard or Dirac basis, I choose beta to be 2 cross 2 identity, 0, 0, minus 2 cross 2 identity, and alphas to be 0, sigma, 0. Okay. Right? Okay. Come back to the equation. Okay. Now we know what are these alphas and betas. Okay. And this also tells that psi must be now 4 component object. Psi 1, psi 2, psi 3, and psi 4. Right? Because 4 cross 4 matrix will act on 4 component vector. Okay. And these are functions of x and t. Each psi 1, psi 2, psi 3, psi 4, each of them is a function of x and t, vector x and t. Okay. Here. Okay. So now let us go back to Dirac equation. So I have I h cross del psi by del t. Now this should be understood as a column vector. Okay. But you will see that this actually it's not a vector. Okay. It does not transform under Laurent transformation as a 4 vector. In that sense, it is not a 4 vector. Okay. It will be clear to you what is this quantity. Slightly complicated quantity. It's not does not have usual transformation rule under Laurent transformation. Okay. So So this is equal to C times alpha dot P. So it is alpha I Pi, okay, plus beta MC square, MC to the power. So C, yeah. So yeah, MC square psi. Okay. So now how to write this equation in a covariant language? That means I want some covariance, okay, like V mu, A mu kind of thing. So I want to write in a tensorial fashion. Okay. Likewise, we wrote the Klein Gordon equation in del mu phi equal to something phi. Okay. It is a covariant. If it holds in one frame, it holds in any other frame. Manifestly, and we can see that it is manifestly covariant in the sense that this is manifestly scalar. Okay. In a similar way, I want to write this equation in a covariant way. Okay. So how to write that? So you can write this, okay, in the following way. Okay. So first you bring this, yeah. First you multiply from the left by beta. Okay. So first you multiply from the left by beta. IH cross beta del psi by del t equal to C beta alpha, C beta alpha I Pi. If there's some more i's implied here, plus beta square MC square. Sorry. Okay. Okay. Now beta square is identity, and now you bring in this entire RHS to the LHS. Okay. So I will get. And I will divide maybe by H cross. Okay. And I will write for P. Okay. So let me write it. IH cross beta del T, this I will write in this way, minus C beta alpha I, Pi is minus IH cross del I, okay, minus beta square is identity, MC square, acting on psi equal to 0. Okay. So this I will write, I will divide by H cross, okay, and I will multiply and divide by C. So this will become, I will multiply C here, divide by C, so it will become del 0. Okay. So I will get I beta del 0. Okay. So this will become plus, so I will take I common. Okay. I beta del 0 plus beta alpha I, okay, del I, minus identity times MC square, entire thing acting on psi equal to 0. So this implies that, so now we define, okay, a 4 vector gamma mu, okay, but it is not a vector, it is a 4 vector in the space of matrices. Okay. So this is defined to be beta and beta alpha I. Okay. Yes. Okay. Gamma mu is defined as beta and beta alpha I. So this I can write with the help of this. I can write this as I gamma mu del mu minus MC. This should be H cross because I divided by H cross. Okay. And I can take C common entirely. Okay. So MC by H cross. Okay. There should be C here. Okay. You can see throughout I will divide by C. So it will be MC by H cross acting on psi equal to 0. Okay. So this is the covariant form of Dirac equation. Okay. Fine. So I will stop here today, okay, and I will start from this onward tomorrow. Okay. So if you have any question, you can ask. Please go through this carefully. Slightly involved. Okay, I did this because I cannot break in between. I cannot take a break in between. Otherwise, it's difficult to understand. So I had to complete in one shot. So this is all steps are logical. Okay. So if you have any question, you can ask. Okay. And before coming to the next class, okay, please read this part carefully. Okay. I will stop if there are no questions. I will stop if there are questions. You can ask.
Sir. Sir, before this Dirac equation, we did the Klein-Gordon equation. So that Klein-Gordon equation was for integral spins, right?
Integral or
integral spin particles.
Okay, it is spin zero. It is basically for spin zero.
Okay. So
there is no angular. There is no spin angular momentum there. I will come to that again. Go on.
Sir, I wanted to ask that what was the need of Dirac equation? What
Dirac equation? Now you will see that Dirac equation. Okay, now since it is first order in time, okay, we will see in the next class that your rho is just psi dagger psi. This is the positive definite quantity. Okay. So the one problem is removed. Okay. So this is the physical reason why Dirac attempted to construct the wave equation, relativistic wave equation, consistent with that E square equal to P square C square plus M square C to the power 4 in this way. This is one of the reasons. And also he wanted to remove this negative energy solution, but there he failed. You will see that although this equation gives you the positive definite norm, positive definite probability density, okay, there are negative energy solutions. Okay? So negative energy problem is plagued with this.
Sir, the
go on.
Sir, the negative energy solutions means they are the theoretical foundations for these exotic particles which were later discovered.
Exotic? What is exotic?
Sir, in the sense means like particles which were not besides electrons and other particles which were not discovered during that time.
So for every particle there is for electron there is a positron. Okay, that was predicted by Dirac, and the foundation for positron is negative energy solution.
Okay, so means this negative energy implies the antiparticle of the.
Yes, in a rough sense, yes, but one has to formalize this.
Okay, sir.
Okay, it's not the only that you have negative energy solution, so you have there is something has to be done. Okay.
Okay, sir.
Okay.
Sir,
any other?
Sir, what is this quantity gamma mu?
Gamma mu's are, see, these are just different way of writing alphas and betas. So I have 4 matrices: gamma 0 and gamma 1, gamma 2, gamma 3. Okay. These are the 4 matrices. Okay. It's a different way of writing this beta and alpha. That's it. Now, what are these betas and alphas? Okay, these are the matrices which come out of consistency relation. These matrices came out of consistency relation. Consistency between what? Between that proposed wave equation and energy momentum relation. Later on, we will see that because of this, your spin, the moment we demand this, your spin has already entered into the picture. The electron spin has already entered into the picture. Okay. So we demand the consistency of wave equation with laws of special relativity. Okay, we automatically get spin. In non-relativistic quantum mechanics, you cannot give a logic for spin. You have to incorporate spin into Schrodinger equation by hand. There is no equation for spin there. Okay, you have to take spin into account by hand. Okay, you have to assume that there is a spin which will interact with magnetic field like S dot B. That term you have to take into account into the Hamiltonian by hand. Okay, but we'll see that the moment I demand the first order relativistic wave equation to be consistent with energy momentum relation, one must incorporate spin into account. Otherwise, it will fail. The theory will fail. But one can have spin half, spin 3/2, etc. But why it is half, that is not fixed, obviously. Okay? But one can, but at least the half integer values, the reason for half integer values will be, the reason for half integer values for spin will be provided. Okay. So please go through this part. It's not trivial. Okay, you have to repeat it several times. The logic behind this. Okay. Fine. So I will stop, and then tomorrow I will take the class. So you have the MMT class at 11:15. Okay. So 11:15 to madam will take till 1 o'clock or something. Okay. I will set I will send a message for that. So I will take class at 9:30 tomorrow, because afternoon you have your internal. Okay. So I will take class at 9:30. Is this fine with all?
Yeah, okay, sir.
No problem.
No.
Okay. Is it for all? Is this okay for all? Those who are having
Yes, sir.
exam also.
Yes.
Okay, fine. So we will meet at 9:30. Okay, 9:30 I may be late slightly. Okay, so 9:30 to 9:45 will start, and we'll end at maybe 10:45 or 11. Okay.